Why do airplane wings bend so much and not break? Ever looked out of an airplane window during takeoff and thought, that wing looks like it's made of rubber? Relax. You're not about to star in a disaster movie. The truth is, modern airplane wings are built to bend, sometimes by several meters, and they're stronger than you probably imagine. That graceful flex you see is one of the keys to keeping you safe, comfortable, and flying efficiently. Let's dive into the science, the engineering, and the surprising tests that prove why wings like those on the Boeing 787 Dreamliner can flex dramatically and never snap. The surprising flex of the 787. On the Boeing 787, the wings can flex upward more than 3 meters during normal flight. Under extreme testing, they've bent over 7 meters without breaking. That's not an accident. It's a product of advanced design and careful engineering. This flexibility starts deep inside the wing structure. At the heart of every wing is something called the wing box, a rigid internal skeleton that runs through the center of the wing, connecting the front and rear spars with a network of ribs. Think of it like a shoebox with strong beams inside. It gives the wing both shape and strength. In the 787, this wing box is made mostly from carbon fiber reinforced composites, materials that are both extremely strong and surprisingly lightweight. Unlike traditional aluminum, which permanently deforms when stretched by less than 1%, carbon fiber can stretch up to around 1.9% before any permanent change occurs. That extra margin allows the wing to bend far more without any structural damage. Why engineers want wings to bend? It may seem counterintuitive, but a wing that bends is better than one that's rock solid. Flexibility absorbs and distributes the stresses of flight, much like how a suspension bridge sways slightly in the wind. A completely rigid wing would transfer more vibration and stress into the fuselage, potentially making the flight bumpier and shortening the lifespan of the airframe. By bending, the wing smooths out turbulence, reduces peak loads, and increases passenger comfort. In other words, that flappy look is part of the airplane's shock-absorbing system. The brutal wing bending test. Before an airplane is ever cleared to carry passengers, it must survive one of the most extreme stress tests in aviation, the FAA wing loading test. Engineers attach hydraulic jacks and weights to simulate forces far greater than anything the plane will encounter in real life. Regulations require the wing to withstand 150% of the maximum expected flight load for at least 3 seconds without failing. For the 787, this meant bending the wings upward a staggering 7.6 meters at the tips. The result? No catastrophic break, just an elastic flex back toward their original shape. This test isn't just a confidence booster. It's proof that the wing can handle far more than any real-world scenario, even in extreme turbulence. Aerodynamics? The longer, the better. One reason the 787's wings flex so much is their high aspect ratio, the ratio of wingspan to average chord width. Longer, thinner wings are more aerodynamically efficient, reducing drag and improving fuel economy. The Boeing 777 has an aspect ratio of about 9:1, while the 787 pushes this closer to 11:1. That extra length means more lift for the same amount of drag, but also greater bending under aerodynamic forces. Fighting induced drag. Longer wings help combat something called induced drag, which happens when high-pressure air from below the wing curls around the wingtips into the low-pressure air above, forming vortices. These swirling vortices sap efficiency and increase fuel burn. By making the wing longer, there's less pressure difference per unit of span, and the wingtips are farther apart, reducing the strength of these vortices. The trade-off? A longer lever arm means more bending moment at the wing root, hence the need for materials and structures that can flex without damage. The supercritical wing profile. A long wing is good for efficiency, but it still needs to hold fuel and handle high-speed aerodynamics. This is where the supercritical airfoil comes in. Unlike the classic teardrop shape you see in textbooks, a supercritical wing has a flatter upper surface, a more rounded leading edge, and a sharper drop-off on the underside. This design delays the formation of shock waves at near supersonic speeds, reduces wave drag, which is a major fuel drain at high subsonic cruise speeds, creates more internal volume for fuel storage. The The 787's supercritical wing allows it to cruise efficiently at about Mach 0.85 without the penalties older designs would suffer. Materials. Why carbon fiber changed everything. In the aluminum era, engineers had to keep wings stiffer to prevent metal fatigue and permanent deformation. Carbon fiber composites changed the game. These materials are built up from thousands of microscopic fibers embedded in a resin matrix, layered in precise orientations. Each fiber is stronger than steel by weight, and when combined, they form a wing that's both light and incredibly tough. Another key advantage, tunable stiffness. By orienting the fibers differently in various layers, engineers can make some parts of the wing more flexible and others more rigid, ensuring the wing bends in a predictable, controlled way. Adaptive aeroelasticity, wings that dance in flight. The bending you see in flight isn't random. It's part of a carefully planned phenomenon called adaptive aeroelasticity. The wing's shape subtly changes under different flight conditions to optimize performance. Takeoff. More flex helps generate extra lift at lower speeds. Cruise. The wing bends just enough to reduce drag and improve fuel burn. Turbulence. Flex absorbs gust loads, reducing stress on the fuselage. This is like a ballet dancer adjusting posture mid-performance. Graceful, precise, and intentional. Handling turbulence. In moderate turbulence, the 787's wingtips can move up or down by as much as half a meter. This movement helps dissipate the sudden forces of air gusts, much like a shock absorber in a car suspension. If the wing were rigid, these forces would be transmitted directly to the passengers and the fuselage structure, causing a rougher ride and more wear on the airplane. The role of winglets. Those elegant upward curves at the tips, or in the 787's case, smoothly raked wingtips, also play a role. They reduce induced drag by smoothing the pressure difference between the upper and lower surfaces. This improves efficiency and reduces fuel burn, but it also changes the way bending loads are distributed. Raked tips extend the effective span of the wing, adding to bending, but also increasing lift, again reinforcing the need for flexible, composite construction. Comparing old and new wing designs. Older jets, like the Boeing 707 or early 3730 models, had stubbier, stiffer wings made entirely of aluminum. They flexed far less, but they also burned more fuel and produced more noise. The efficiency trade-off was huge. Today's wings, especially on aircraft like the Boeing 787 and Airbus A350, are longer, thinner, lighter, and far more flexible, resulting in 20 to 25% fuel savings compared to older designs of similar size. Extreme testing beyond the FAA. Beyond the standard FAA requirement, manufacturers often test wings to the point of actual failure in controlled conditions to understand exactly how and where they will break. This data helps refine future designs and ensures that, in real-world flying, there's an enormous safety margin. For the 787, the wing didn't fail until well past 150% of the maximum load, meaning that in normal flight, it's nowhere near its breaking point. Passenger perception versus engineering reality. From a passenger seat, wing flex can look alarming, especially during takeoff or in turbulence. But to an aerospace engineer, that motion is a reassuring sign that the aircraft is behaving exactly as intended. The truth? A bending wing is safer than a stiff one. It's absorbing and distributing energy instead of concentrating it in one spot. The future. Even more flexible wings? Research into morphing wings, designs that change shape more dramatically in flight, is already underway. NASA's X-plane projects are experimenting with wings that twist or extend at different phases of flight to achieve even higher efficiency. With advances in composites, smart materials, and real-time computer control, future wings could make today's 787 look stiff by comparison. Final descent. The reason airplane wings bend so much without breaking boils down to three main factors. 1. Advanced materials like carbon fiber that can flex significantly without damage. 2nd, aerodynamic designs that favor longer, thinner wings for efficiency, which naturally bend more. 3rd, engineering precision that tunes flexibility for safety, comfort, and performance. So next time you look out at the wing swaying gracefully against the sky, remember, it's not a flaw. It's one of the most impressive feats of modern engineering. The airplane isn't just flying, it's flexing its muscles,